SN1 substitution and E1 elimination reactions involve a common carbocation intermediate, and this carbocation can be susceptible to 1,2 rearrangements. My advice to you when you know you're in an SN1 and E1 context is to think mechanistically and be very careful with the carbocation intermediate. Always consider the carbocation and generally go by the rule, if a carbocation can rearrange to a more stable cation via 1,2 rearrangement, it will do so, and quite frequently the product following rearrangement is actually the major product, although as in many things in organic chemistry, in practice, this can be a little bit difficult to predict. So let's consider the two reactions here, which involve solvolysis of a secondary alkyl bromide. When we take this alkyl bromide and we put it in water and we heat, we get a mixture of not one but two substitution products. Let's call them 1 and 2. And we get elimination products as well. Now, to consider where 1 and 2 come from, let's look at 1 first. 1 is the relatively simple SN1 substitution product derived from loss of the bromide and water coming in as a nucleophile, and then we lose a proton from H2O to give the alcohol product. So 1 is derived from simple SN1 substitution via this cationic intermediate right here. This is a secondary carbocation, and so we should be alert to the possibility of carbocation rearrangements taking place and consider whether a neighboring hydrogen or methyl group could migrate to produce a more stable carbocation. One thing we'll notice here is that we have a CH bond that could migrate, leaving positive charge at this carbon and 3 alkyl groups attached to that carbon. When that rearrangement occurs, we end up with a tertiary cation that's more stable than the secondary cation that we started with. And in fact, this tertiary carbocation leads to product 2. When water coordinates to this cationic center, followed by loss of a proton, we end up with product 2, and I encourage you to pause the video and draw curved arrows out for that to make sure you can see it if you need to. In the second case, we've got a similar secondary alkyl halide substrate reacting with water upon heating, and we get not 1 but 2 substitution products as well as elimination products. The first substitution product, if we call that 3, is derived from the carbocation that forms after loss of bromide. So we get this carbocation, water comes in here, we lose a proton, and we end up at alcohol 3. However, again, it's a secondary carbocation, and we need to consider the possibility of rearrangement to a tertiary carbocation. That can occur in this case with a methyl group migrating rather than a CH bond. And after this 1,2 rearrangement, we end up with a tertiary cation that's more stable than our starting secondary carbocation, and reaction of this tertiary carbocation with water leads to product 4, the rearranged substitution product. And again, that's worth pausing the video and drawing curved arrows out for those 2 steps, the nucleophilic attack followed by the proton transfer, if you need to. So the moral of the story here is, in SN1 and E1 reactions, you always want to consider and often explicitly draw the carbocation intermediate that forms in these reactions. And if a rearrangement via 1,2R can take place, it will to produce a more stable carbocation and often a more highly substituted product than we would get from direct SN1 substitution without rearrangement. Rearrangement can also be important when a resonance-stabilized carbocation can form. I won't show an explicit example of that here, but it's something to keep in mind that CH or methyl or other groups can migrate to produce a resonance-stabilized carbocation in some cases, and those rearrangements are heavily favored in the forward direction, and the products we get are derived from those resonance-stabilized carbocations rather than the less stable initially formed carbocation. Neopentyl alkyl halides react very slowly in SN2 reactions and cannot react in E2 reactions due to the lack of beta hydrogens. However, they can react under solvolysis conditions with weak nucleophiles in solvent quantities like water and alcohols. When we take, for example, neopentyl bromide and put it in the presence of water and heat, we do not see this primary alcohol product, this neopentyl alcohol. This would involve presumably an SN2 type elementary step, which we know is prohibitively slow due to the steric hindrance provided by this tert-butyl group. In fact, the only product we see is this tertiary halide that seems to be derived from some kind of a rearrangement. What's the mechanistic rationale here? Let's draw a mechanism for this reaction. Given that we have only a weak nucleophile here, and we know that SN2 is prevented by the steric situation, our first instinct may be to just kick off the bromide and produce a carbocation. However, that carbocation would be primary, and this is a prohibitively unstable reactive intermediate. No primary carbocations allowed in organic chemistry. What happens instead? How do we get this rearrangement without formation of a carbocation? Here's a case where two elementary steps can actually occur in one, or two electron flows, if you like, can occur in a single elementary step to go right to the rearranged cation without the intermediacy of a primary carbocation. We can do the loss of a leaving group and 1,2 rearrangement in a single elementary step. Via electron flow like this methyl group can migrate and the bromide can depart in a single elementary step. This gets us right to a tertiary carbocation without the intermediacy of a primary carbocation, which is implausible due to the instability of these cations. So we're now right to a tertiary carbocation, and if you compare this to the rearranged tertiary alcohol product, you'll see that the only difference is we've got a carbon-oxygen bond at this center that's cationic in the cation. And so water then coordinates here in a nucleophilic attack step, and we lose the proton from water to give the neutral alcohol product. So neopentyl halides are a nice example of rearrangement in action. The unique thing with these is that to avoid a carbocation intermediate that's primary, they rearrange simultaneously with loss of the leaving group.